Hey guys, today we're going to be looking at dependent and independent events. Okay, we briefly spoke about it last time when we were talking about conditional probability, but just a little bit more clearly, two events are independent if and only if the probability of A given B is still just the probability of A, and probability of B given A is equal to probability of B, because independence is where the probability of one does not impact the probability of the other. This also impacts our multiplication rule, okay, which I've written afterwards here. Probability of A and B is probability of A given B times by the probability of B. But if we have independent events, then this part is just the probability of A, so we can multiply those two. So this rule up here, or this one here, can be working in two different ways. If we can show that these situations result in the probability of A given B is equal to probability of A, and probability of B given A is equal to probability of B. If we can show that that's true, or we can show that the probability of A and B is equal to the probability of A times by the probability of B, or all three, then we have shown or proved that these two events, A and B, are independent. Otherwise, if we are told that two events are independent, or we can know that they are independent, like rolls of a dice, which we'll get to in a second, if they are independent, then we can use the multiplication rule pretty quickly to help us solve some different issues or different problems. So, quick example. A fair dice, 8-sided dice, is rolled twice. What is the probability of two ones? So we're looking at the probability of one and then another one. Now the probability of getting one on an 8-sided dice is 1 out of 8. And so because this is happening twice and each roll of the dice is independent, that first roll doesn't actually change the probability of that second roll, which some people can struggle to get their head around. Is that 1/8 times by 1/8, because they're both the same probability, and we get 1/64. So we've just used our multiplication rule to help us solve that problem there. So let's go to the top of the page rather than somewhere in the middle there. Example 13. Assuming boys and girls are equally likely, what is the probability that in a family of 5 children, all of the children will be girls? So boys and girls are equally likely, so probability of having a girl is a half, and the probability of boys and girls don't impact one another, usually speaking, or on a global kind of scale. Might work differently for different families, but it's neither here nor there for our stuff. Probability of girl and girl and girl and girl and girl for 5 times, we've got half multiplied 5 times, or if you wanted to, you could say it's half to the power of 5, and that makes 1/32. Okay, last example here, we're going to look at a box of dice has 5 red, 5 green, and 5 white dice. If the dice are chosen at random, find the probability of 3 green in a row if the die is replaced before the next is taken. So with that replacement, the probability of getting that next dice doesn't change, because there's going to be 15 dice and there's going to be 5 of each color with that replacement there. So we've got independence here. So picking that first green is 5 out of 15, or 1/3. Second time, it's still the same. And then the third time, still the same. Now this is just 1/3 times 1/3 times 1/3, and so you'd get 1 out of 27. Now this one's a little bit different, and I figured I'd go over a couple different ways of doing this. We've got the probability of 3 green in a row if they are not replaced. So now we have dependence. Without that replacement there, the probability is changing. Once you take out 1 green dice, you've only got 14 left, and so that's changing the probability for all of our situations, as well as the green, of which we have 1 less. So without 3 green, what we are looking at is that the probability of a green, given that there's already 2 taken out, times by the probability of a green, given that there's 1 taken out, times by the probability of green when none have been taken out. So that's our conditional probability formula that we've been using last lesson. But we can look at this in a couple different ways. So we can look at this as a tree diagram, if we would like. So as the probability of green changes, it starts out as 5 out of 15, then we take a green, which means we've got 4 out of 14, then we take another green, which is 3 out of 13. So this is what your actual answer would be: 5 out of 15 times by 4 out of 15 times by 4 out of 14, and then 3 out of 13. Okay, let me just fix up that 4 to make it a little bit clearer. 14. 4 out of 14 there. Alright, and if you're clever, you might remember that we can do this in a choose manner. Okay, this is less about our independence, but because we've got without replacement here, how many ways can I choose green out of the 5 if I'm picking 3? There is 5, choose 3 out of, and then I'm choosing 3 out of 15, so 15 choose 3, and that would give us our same answer as this times together of our conditional probabilities. Anyway, short video today. I hope that helps with the exercise, and let me know if you've got any questions.